Okay, welcome in folks from the future. In this problem solving session, we're going to talk about quiz 4-1. So we've got a person in space, they got a rock and a watermelon. I think it'll be a good one. Okay, so this is another problem on 2D momentum, or actually this one may end up just being 1D overall. Let's give it a look. No, it'll be 2D. Let's give it a look. You're in outer space, drifting to the right as shown in the picture. You happen to be holding a heavy rock. There is also a stationary watermelon floating in space, and you're really craving fresh fruit. Let's go. You really wish to grab the watermelon and get back to your spaceship. Getting back is important. Typically, this would be wishful thinking, but thankfully, you've taken physics 7B and know exactly what to do. The rock has mass m. Let's go ahead and label that. The watermelon has mass 2m. My mass is 9m. Below, use momentum charts supporting for explanation, show all steps and calculations. So, move this on over. You drift while holding the rock toward the watermelon with an initial speed of 1.2 meters per second. When you reach the watermelon, you grab it. Use a momentum chart to help you solve for your velocity after you grab the watermelon. Note, the watermelons and your position should have the same y value. No, here we go. The watermelons in your position have the same y value. Okay, cool. That makes life easy. So, as I'm drifting toward the watermelon, I have 1.2 meters per second of speed. When I reach the watermelon, I grab it. Let's go ahead and we'll use a momentum chart for that, and that's fine. Okay, so my initial frame here is before I've grabbed the watermelon. My final frame is after I grab the watermelon. So before, haven't grabbed it yet. No watermelon. Sad face. Yes, watermelon. No watermelon. Afterwards, I'm happy. I had the watermelon. Okay. All right. So I'm going 1.2 meters per second to the right initially. Sorry, folks, playing around with my computer for a second. Okay, 1.2 meters per second to the right initially. So my initial momentum vector for just my body points to the right and has a magnitude that is 1.2 times 9. Yeah, and let's do the rock in there as well. We'll do 3 parts. Let me pin the things that are here. Okay. We've got 3 parts. I'm going to have body, rock, and watermelon. Rock, melon, sweet. And I will have a total at the bottom, total. Okay, so here's P initial, here's delta P, and here's P final. So initially, my momentum is directed to the right. My body's momentum is directed to the right. I have initial speed 1.2 meters per second. So here we go. That thing has magnitude 9 times 1.2, which I should have known is 10.8. So the length of it is 10.8. I'll just make a note of that over here. So PI for the body, magnitude is 10.8. Okay, for the rock weighs mass M. Cool. Oh, this should be 10.8 M. There we go. The momentum for the rock is going to be pointing in the same direction as me and 1/9 as large because it weighs 9 times less than I do. So P initial for the rock magnitude is just 1.2 M. And then there's some units on top of that. So it'd be 1.2 M meters per second. But I'm going to drop the units for now. Okay, and the melon is just floating out there in space. It has no velocity. So it has no velocity, and as such, its momentum is 0. Everybody with me so far? Does this setup look okay? Got a chat coming in. Okay, looks good. All right, fine. Let's keep the party rolling. So, oh, I made a spare mark. There we go. All right. So let's talk about delta P's here. When I reach the watermelon, I grab it. I use momentum chart to help solve for the velocity after you grab the watermelon. So I still got the rock. I still got the melon, or I now have the melon. My body is still moving to the right. So when I hit this stuff, my total momentum is going to be conserved. So I'm out here in space. I got no net external forces. So my delta P is going to be 0. I've tried to draw in this total initial momentum as being larger than either of the individuals because they're both pointing in the same direction, to the right. That means that over here, I'm going to also have a long rightward momentum vector, same size. Okay, so when I hit the rock, what do I do? Or sorry, when I hit the melon, what do I do? I hit the melon picks up some speed to come with me. So the melon is now going to have some final momentum, unknown size. Whatever size momentum the melon has, the rock is going to have half of that because we're still stuck together. Like everybody's still together. The rock and the melon and me are all still stuck together. So V final for everybody is the same. V final of my body is the same as V final of the rock, is the same as V final of the melon.
Doesn't that make it doesn't that make it elastic if they're all the same, but then, or sorry, if they're all sticking together, they're inelastic, but then there's no net change. So like I'm confused.
Yeah, sure. So it is inelastic in the sense that they're all sticking together. That's right. If they're in an inelastic collision just tells me, yeah, I guess, so let me kind of get feedback from you a little bit, I guess. Inelastic collision basically is the least efficient possible collision that preserves momentum. So all collisions preserve momentum. All collisions, sorry, in force-free environments. So all collisions where you don't have a net external force, those preserve momentum. But elastic and inelastic talk about kinetic energy. So inelastic collisions make kinetic energy as small as possible. So sticking everything together makes the kinetic energy drop as much as possible. You lose a lot of energy as heat. Elastic collisions, you lose no kinetic energy. So you don't lose any energy as heat. Here, the fact that it's inelastic just lets me know this, that they have the same velocities at the end. Does that help, or is that still a little sketchy? What are you thinking about the inelastic or elasticness of it?
No, it makes more sense now because I always forget about the the thermal energy that like leaves the system, and I'm always
Yeah,
wondering why there's some sort of like equality to it, but that makes sense.
yeah, it's just two different things that are conserved. So the momentum is always conserved, and the kinetic energy is sometimes conserved depending on if it's elastic or inelastic or not. So it's not that it's irrelevant whether this collision is elastic or inelastic. It's just that the inelasticity of it only really matters to me insofar as it lets me say that the velocities of all of them are the same at the end. So I'm not making any direct claims about kinetic energy here, just that the velocities are the same at the end. Thanks for the question. Okay, so the final momentum of the body also points to the right. It's now going to be a little bit less though, right? Because I've run into a rock. I need for the sum of these three to add up to this long blue vector, the long light blue vector. But the melon used to be 0 and now points to the right. So the other two have to kind of take a hit. They have to reduce in speed. Okay, so the change in momentum for the body is going to be to the left somewhat. For the rock is going to be to the left somewhat. For the melon is going to be to the right somewhat. Cool. So now we can just write down the equation if we like. So the goal is to solve for the velocity after we grab the watermelon. So we're interested in the velocity of the body after the watermelon, which is the same as the velocity of everybody else. because they're all stuck together. Okay, so what do I have? I have P initial of the body plus P initial of the rock plus P initial of the melon equals P initial of the or P final, sorry, P final of the body plus P final of the rock plus P final of the watermelon. Okay, so this is my conservation of momentum equation. It tells me that the initial and final velocity, or the initial and final momenta are the same. The total initial and total final momenta are the same. So to write this maybe like one step back, this is that P initial equals P final and total and total. Which again, to pull this even one more step back, is that delta P total equals 0. These are all equivalent statements. These all say the same thing. Okay, so now that I've got that, each of these corresponds to a term on the left side of the momentum diagram. Each of these refers to a term on the right side of the diagram. So let's go ahead and just draw in those vectors now. So the initial momentum of my body has units like this. It is 10.8, 0. I'm going to the right, 10.8. Yeah, and then I'm gonna have to multiply all this stuff by an m, but that's all right. So I'm dropping units here for a moment. Plus the initial momentum of the rock, which is going to be 1.2, 0. This is just 9 times smaller than me. 1.2, 0. Plus the momentum of the melon, which is 0. Okay, and that's going to equal whatever my right-hand side is. So let me first solve the left-hand side, just for space purposes, and then we'll say what the right-hand side must look like. So for the left-hand side, this is 10.8 plus 1.2 plus 0, comma, 0 plus 0 plus 0, which is, it's going to be 12, 0. And now I'll bring back that unit that I was neglecting up here. So it should be an m modifying all of these, m, multiplying them all. So it's 12, 0 times m. That's my initial momentum. Pi total is this thing, 12, 0. Is that all right? All with me? P initial, momentum initial. I'm happy to run it back a little bit too if there's something strange going on, or if that's not like, how do we get here kind of thing. Okay, most of the feedback I'm getting right now is positive, but if you're having trouble, please do let me know. I'm trying to go at a reasonable pace, to like slow enough that I can still say reasons for everything. But I'm probably going to slip up on that. So if you have questions, really, please do answer, or please do let me know. Okay, so we've got 12, 0. Nice. Now for the rock, or not for the rock, sorry, that's the total. So now I'm interested in the right-hand side. I've found the value of this big light blue vector here. Do I have to write it in component form if it's just moving in the x direction? No, I could have written it not in component form, since I knew they're all traveling to the positive right direction. That's okay. The reason that I wrote it in this form is just so that I can be extra explicit that each of these is a vector, and they're each corresponding to these individual elements of our first column. Yeah, and the total is this vector here to the right. But like in terms of, could I just add 10.8 and 1.2 and be all right? It's like, yeah, you'd be all right. Yeah, it's just 12, 0. Yep, sure thing. Okay, so I've got my initial momentum. That's going to be the same as my final total momentum. Boom. So let's talk about that final total momentum on the right side, which I'm going to write in green for color coding's sake. So P final total has got to be the same as P initial total. All right, but let's look at P final total in a little more detail. So P final total, now everybody's moving at the same speed. So, and everybody's moving in the X direction. So the total momentum is just going to be M person plus M rock plus M watermelon, massive melon, okay, times the velocity final, comma 0. So take a look at this if it's not immediately clear why. So if you kind of distribute the velocity in, you can see it's massive person times velocity, that's the momentum of the person, massive rock times the velocity, that's the rock's momentum, and massive watermelon, massive melon times the velocity. So summing up all those things together gives me the total momentum. If you like, maybe I kind of skipped a step here. I just simplified it before actually, what do you say? Before actually doing it, before writing it down. Okay, so boom, there we go. So now I have everything I need to solve for that V final, because there's V final right there. And these two things have to be equal to each other. So 12 comma 0, the initial momentum has to be equal to the final momentum. So the person plus the rock plus the watermelon is 9 plus 2 plus 1, 9 plus 2 plus 1, or sorry, 9 plus 1 plus 2, I think. Which one weighs more, the watermelon or the rock? The watermelon weighs more than the rock. All right, good stuff. Comma 0. And there should be a VF there. Here's V final, comma 0. So now I can just solve back for V final by component. So this is going to be 12 on the left and 12 on the right. So V final is just going to be 1 meter per second. That's convenient. I'm sure nobody custom tailored the problem to that number. So 1 meter per second. And there's part 1. Now, of course, in practice, quizzes go by a lot faster than that. So yeah, so I took a lot. I was very explicit about showing all my steps here. In practice, it would be ideal if you could hop to this step, like do that step pretty darn close after you draw in the momentum diagram. And then from there, it's pretty quick. Okay, more questions on that. Questions. The next part is when it gets 2D. Okay, let's charge on down to B here then, or part 2. Once I have the watermelon, I throw the rock, after which, this is not going to be a complete sentence, after which you are traveling while holding the watermelon toward the spaceship with velocity in the x direction of Vx equals negative 1 meter per second, and the y direction of Vy equals 1.5 meters per second. I was right. Okay, it's fine. So use a momentum chart to help you calculate the speed of the rock after you threw it and angle its velocity makes the x-axis. Okay, so 2 things we're looking for. One is the speed, which is the magnitude, the speed of the rock after I throw it, and the angle its velocity makes with the x-axis. So I'm looking for the, how do you say this? The magnitude and direction form of the velocity vector of the rock. That's what I'm looking for. So I need to get at the rock's velocity. In order to do this, I'm going to again have to use conservation of momentum. Okay, so it's me and the watermelon now. I'm going to simplify my life just ever so slightly. I'm going to say that me and the watermelon form a single system. Me plus melon form a single system. Yeah, that'll just make my diagram slightly simpler. I also could do it keeping them as 3 bodies. Just since we have like 10 minutes left, I'm just going to keep it as me and melon for now. So me plus melon form 1 body, and the rock will be my other body, the other thing in my momentum chart. Ugh. Tongue twisters at 8:50. So again, the reason that it's okay for me to think of the melon and me as being a single body is because we're just traveling with one another. Yeah, we're just traveling with one another both before and after the interval. Is that okay? Does that make sense too? All right, so again, if you're typing, please do keep typing. I'm wanting questions here. But so if I've got this initial and final momentum of my watermelon and the rock, me plus watermelon and rock system, I can start to draw in some of these vectors. So again, just to be super explicit, the before is I have the watermelon all traveling together. Everybody traveling together. Yay. Big happy family. We got watermelon and rock and person all hanging out in space. All right. The after is the rock alone and me and the melon headed back to the ship. Poor rock. Okay. So let's talk about the totals and the individuals. So here's the total momentum. Total momentum is going to be the biggest one initially. It's pointing just to the right as before. Now remember, everybody initially is moving 1 meter per second to the right. So I can just straight up calculate each of these individual momenta. So initially, now that we're all traveling 1 meter per second to the right, me and the melon, our combined mass is 9m plus 2m makes 11m. So we are pointing to the right with a pretty big momentum vector. P initial of me plus melon, mm. Magnitude of that is 11m. Okay, for the rock, now the rock weighs 1m. So its initial momentum is going to be a lot smaller, pointing in the same direction. Momentum initial of the rock, magnitude of that is 1m. 1 meter per second times 1 m for the rock's mass gives me 1m as my magnitude of momentum. And each of these, it has extra units on top of meters per second, meter per second. So m has units of kilograms, meters per second for each of those velocities we multiplied. I'm going to erase these because I feel like those are going to be confusing later with multiple m's mixed in when some of their variables and some of their units. Okay, more questions, more questions? Where's my tea? Oh, there it is. Okay, so in terms of the final momenta then, so the final momenta is just given to us. So we know the rock's final velocity, the, wait, hang on, sorry. We know the me plus watermelon's final velocity. Vx is -1 meters per second, Vy is -1.5 meters per second. So in the end, I'm moving something like this with my watermelon. Nice. That means the rock is going to be moving some other direction. So let's fill in the lower part of our chart first. We're still out in space. There's still no net forces on us. No net forces that are, non-negligible. So my final momentum is going to be the same, which means that my change in momentum is, how do I say this? My change in momentum becomes the part that is constrained. So the change in momentum is the change in momentum of the rock has to be equal and opposite to the change in momentum of the me plus melon in order for the total momentum change to be 0. So I can kind of just directly calculate the change in momentum of the me plus melon system because I've got the final, I've got the initial. So the change total for this is going to look something like this. It's going to be a long vector, points mostly to the left and some down. For the rock, it's going to be the opposite of that. Long vector. Now, when I'm drawing in this delta P here for the me plus Melon system, I'm being careful that the y component is only as long as it is for my final. So I'm making sure that the y component is only that long, because the initial momentum vector only has an x component. So the two things that I'm trying to make sure that I do when I draw in this delta P here is that I match the right size of my y component, and I'm sure that my length in the x direction is longer. Because in order for me to pivot from going mostly to the right to going mostly to the left is to have a horizontal component that is longer than either of the individuals. First, I have to get back to 0 in the x direction, and then I have to go a little bit further. Okay, now for the last one, I can just add up P initial plus delta P of the rock. That's going to give me a momentum vector that is slightly longer in the x direction. I got a question, which is, how did you determine the angle of PF for the me plus Melon system? So the way I determined the basic direction, the general direction of it, is by knowing these two components, -1 meters per second and -1.5 meters per second. So since they're both negative, it's going to be pointing to the left and down. And then since Vy is larger than Vx, I know it's going to have a slightly more of a vertical component than a horizontal component. So actually, I maybe should draw it even a little bit steeper. There we go. Something like that. That might be better. Yeah. Does that make more sense? Okay. So I kind of just did that sort of from the components themselves. You could also do tan inverse of the thing and just make sure you're in the right quadrant, right? So make sure that you're both in the negative x and the negative y side, and then tan inverse of 1.5 over 1 would give you a nice angle measured relative to the x-axis. Okay, we're just about at time. Let's do this. So I'm just gonna do a sketch for it, and then I'll solve it very quickly. So same deal. P initial has to equal P final. So the mass of me plus the rock is 11. So it's going to be 11 comma 0 for me plus rock, or me plus Melon, plus 1 comma 0 equals, this is the initial momentum, equals, now it's going to be me plus rock afterward is going to be 11 times -1. So it's going to be -11 comma, oh, and then what's 11 times -1? It's like 15.5. I think that's right. -11 times 1.5. 16.5. Wow. Year 4 grad school, can't do multiplication. Okay. Plus whatever the final momentum of the rock is. That's the thing we're interested in. So now I just do this out. 11, 1, that's 12, comma 0, is equal to -11, comma 16.5, -16.5 plus P final for the rock. If I do that vector subtraction, yeah, sure thing, Jordan. If I do that vector subtraction, I get 23, comma 16.5, which is the final momentum of the rock. Dividing by the mass of the rock gives me velocity. So since P divided by mass is velocity, or in other words, P equals mv, then I can divide by the mass of the rock, which is 1, to find that the velocity of the rock is 23, comma 16.5. Quick intuition check. I double check that against the rock's momentum vector, and it points in roughly the right direction. Okay. I know that was kind of a quick sketch toward the end. It ends up being basically the same as the first part. It's just in 2D now. So I do the same thing twice. Instead of only adding in the x direction, I add in the y direction as well. That'll get me out the final velocity of the rock. Or this is the component form. So to find the magnitude and direction, the magnitude I get by squaring the elements and square rooting them. So 23 squared plus 16.5 squared. Square root of that is 28.3. And then the direction I get by tan inverse of the y over the x, so 16.5 over 23. Which is 35.7 degrees. Okay, I'm going to leave this up for a second. Feel free to screen clip it, but I probably will go ahead and call it there. We're already about 3 minutes over. So I'll stick around for a minute or two here for questions, but y'all shouldn't feel obligated to hang out. Thanks, everybody. Sorry the quiz was a bit rough. Yeah, I don't know. I'll have to take another look at it and see if there's something that I should have done differently. To be honest, I sort of was hoping that this one wouldn't be too bad, but clearly there were 1 or 2 questions that really threw us for a loop. So I'll reframe. Thanks, folks. All good, more questions? Yeah, of course. Sure. And all right, if you've been joining us online, thanks.